होतोय सर.
Did you getting my voice? Now did you getting my voice?
Yes, sir.
Okay. See, in the last lecture, we have seen the concept of DC load line. In that case, what we have to do, we know that in case of DC load line, there is a 2 point with respect to DC load line. One is upper point, other is lower point. On that point, we have to be draw the one of the line that is called as DC load line. We have seen this DC load line. This is nothing but a DC load line. This is the DC load line. Means position of this point, upper, mid, or lower, accordingly, particular application we have to be decided. This is nothing but operating point of your configuration. See, for that purposes, we have seen the concept of DC load line with respect to this configuration, right? This is the configuration of the diagram for the concept of DC load line. Above figure shows that VCC is power supply applied to the collector, and other power supply VBB is applied to the base, right? We are applying this to voltage and apply the KVL. KVL will indicate that Kirchhoff's voltage law to this configuration. Accordingly, by applying the KVL, we have seen that we have to be apply the KVL two side, either your input as well as output side. Initially, it is applied to the output side, that is a KVL to the output side. So start up with the plus VCC, it is a plus point, plus VCC traveling towards the here. Upper point is plus, second point is negative. So plus VCC minus of IC into this RC, right? IC into RC, and voltage coming across it, it is a second point VC. So plus VCC minus of IC into RC minus of VC. This is equal to 0. This is the equation. After all that, we have taking out the IC into RC another side. So IC into RC negative going here as a positive. So VCC minus VC, which is equal to IC into RC, right? So we have to be separate out this IC and this RC. So VCC minus VC divided by RC. This is the equation coming with respect to IC. See, this is the equation. Now see, this is the equation of your load line, but we have to be separate out this equation, right? For that purpose, 1 by RC is taking in this way, and this VC and VC taking on another side. So minus 1 upon RC. See, VC we are taking first, minus 1 upon RC into VC. See, minus 1 upon nothing. That's why it is a 1. So minus 1 upon RC. This is the problem of the network. See, concept of DC load line seen by this diagram. So for that purposes, we have seen this equation is equal to VCC minus VC divided by RC. So minus VC, we have taking here minus VC. आता येतोय का आवाज? आता आवाज येतोय का? हॅलो, आवाज येतोय का आता? प्लीज गिव मी रिप्लाय. क्लियर आवाज? आता आवाज येतोय का? Did you getting my voice?
ब्रेक होतोय सर.
नेटवर्कचा इश्यू काहीतरी दिसतोय. आवाज कसलाच येत नाहीये. हॅलो, आवाज येत नाहीये का?
ब्रेक होतोय सर. ब्रेक होतोय.
नेटचा इश्यू असेल, होईल आणखीन पाहू आपण. पण थोडा तरी आवाज येतोय का ब्रेकच होतोय सारखा? हॅलो हॅलो
तर थोडा नाही, खूप ब्रेक होतोय.
सर काय कळत नाहीये, ब्रेक होतोय आवाज.
इंटरनेटचा इश्यू, आता काय करायचं सांगा. मधूनच जात आहे, मधूनच येत आहे. हॅलो, बघूया आपण. ज्यावेळेस काहीच आवाज येत नसेल त्यावेळेस मला हे करा. चालेल. हॅलो हॅलो, आता काहीच येत नाही आवाज.
येस सर,
ओके ओके.
येतोय आता.
Now apply QL to the output side. We have to see that this is the equation IC equal to VCC minus VC divided by RC. So minus VC we are taking first. So this is a minus VC and here is no anyone. That's why it is a 1 divided by RC. So minus, that's why minus 1 upon RC into VC. This is the thing with respect to this type of configuration. Now see, this is a positive. So plus this VCC divided by RC. This is the equation with respect to your this configuration. We have seen here. See, we have seen here. This is the equation how it is formed. Y is equal to mx plus c. Now see, this is the equation, operating point equation with respect to this type of configuration. Now see, for that purposes means we have seen this equation. See, this is the equation, right? This equation is nothing but a minus 1 upon RC. VC plus VCC upon RC is same as like as Y is equal to mx plus c. So in that equation, Y is indicate that IC, M indicate that 1 upon RC, X indicate that VC, C indicate that VCC by RC. See here. This is the thing with respect to this type of configuration. Now see, we have to be put out. See, in this equation, if we have to be put out VC, see, put out VC equal to 0. In that case, you got the equation that is a IC equal to VCC upon RC. And when we have to be put out the IC equal to 0, that is another thing. See, put out IC equal to 0. In that case, we got the equation such as VC equal to VCC. So we got 2 point, IC equal to VCC by RC and VCC equal to VC. We have draw one of the line on that 2 point, that is nothing but a load line. See here. This is nothing but a VCC by RC. This is nothing but a VC equal to VCC, right? On that two point, we have drawn this line. This line is called as operating line or the load line, right? This is the thing with respect to operating point. See, operating point decided how the particular device should work. See, when operating point position is towards here, it should be act as a cut-off region. When it is at the center of the load line, right? Center of load line. In that case, it should be worked as amplifier. When it is at upper position, it should be act as a saturation point. Means when it is a cut-off region, it should be act as a open switch. When it is a saturation region, it will be act as a closed switch. That is the thing with respect to the operating point relationship with respect to the operation of your transistor. See, now according to the position of the operating point, this is the actually position of the operating point, right? 3 position, right? There are 3 operating region of your transistor. One is nothing but a active region, other is cut-off region, third is saturation region. See, in active region, if this is your nothing but your load line, see, load line, here one of the point, here one of the point, right? Here point is nothing but a VCC by RC. Here is nothing but here is the VC equal to VCC. It is a VC equal to VCC and it is a nothing but a VCC by RC. This 2-point line, we have to be draw the line. If the Q point position is center of load line, it should be act as a amplifier. If the position of the Q point is near about the VC, it should be act as a cut-off region and it should be act as a open switch, right? This configuration, center of load line indicate that it should be act as a amplifier. Now see this configuration, if the position is upward, upward towards the saturation region, it indicate as a close switch, right? This is the thing with respect to the DC load line and their position. See, when the DC load line position is center of load line, it should be act as an audio amplifier. When DC load line position is towards the downward, that is just near about the VC, it should be act as a cutoff switch. When it should be towards or upward the IC, in that case it should be act as a close switch, right? It is in a saturation region. This will be the thing with respect to the load line and their position. Accordingly, particular configuration should be worked on. Selection of Q point, right? Selection of Q point indicate that depending on the application of the particular thing, we have discussed the same thing. When the device work in a cutoff region, I have told you, its cutoff indicate that device is normally off, right? This is nothing but act as an open switch. When device voltage and current is full, that is saturation state, in that case your device should be worked as a close switch, right? When amplifier, see, when the position of the load line is center of load line, see, center of load line, it should be act as active region, and its application of it is as like as amplifier, right? This is the thing with respect to the operation of the particular configuration. See, this is the actually load line. See, load line indicate that it is the plot of VC, means collector to emitter voltage versus collector current, right? According to the position of this point, right? According to position of this point, it should be different application, right? When the position of the load line is center on the load line, it should be act as a active region. It is nothing but a device should be act as an amplifier, right? Audio amplifier, usually in a many more function, right? So cutoff region indicate that when their point, operating point is just near about the VC, in that case device act as a cutoff region, right? Cutoff region, or it should be called as fully off position, right? So if the position of Q point is towards the upward, that is towards the saturation region, then in that case your transistor is fully on, right? So in that case it should be act as a closed switch, right? Here it should be act as an open switch. This is decided that the particular application, and according to their particular graph indicate that position of Q point, lower position of Q point, it indicate that it should be act as a fully off, or it should be act in a cutoff region. It is in a center, it should be act as a active region or the audio amplifier. Or if the position is towards the upward, in that case it should be act as a saturation region or the fully on, right? This will be the thing with respect to the particular operation of the transistor and with respect to your Q point position. Now see, why we need of the biasing. See, we have discussed biasing means what? See, applying voltage to the respective terminal of transistor to work in a particular condition, right? So biasing, why we need a, see, to work in a particular condition, we have required the certain amount of voltage. To provide the certain amount of voltage is nothing but a biasing of your transistor, right? And why we need of the biasing? See, we have seen the three type of the Q point. Three type of indicate that one is your off, means fully off indicate that cutoff region. Then middle point indicate that it is active region, and the upper point, that is a saturation region, right? These are the three operating point of your transistor. According to these three operating point, device should be worked, right? So that when we have to be worked in a lower, that is cutoff region, in that case your device should be worked as a fully off, right? Fully off during cutoff region. When it should be at the center of load line, it should be act as a audio amplifier, right? And when it is to upward indicate that saturation region, it should be act as a closed switch, right? These are the application. So for that particular application, we have requirement of the Q point should be stable, that should not be changed towards the upward or towards load. It will be at the particular location, right? The position should not be changed. आता लक्षात घ्या, बायसिंग करायचं म्हणजे काय असतं, आपण व्होल्टेज ट्रान्झिस्टरला अप्लाय करायचं, बरोबर? ते ट्रान्झिस्टरला जेव्हा व्होल्टेज अप्लाय करायचं ना, जर समजा मला अँप्लिफायर यूज करायचं असेल तर त्याची पोझिशन सेंटर ऑफ लोड लाईनलाच असायला पाहिजे. जर मला क्लोज स्विच करायचं असेल त्याची पोझिशन टुवर्ड्स द सॅच्युरेशन रिजन मध्ये असायला पाहिजे, किंवा तो कट ऑफ म्हणजे ऑफ करायचा असेल तर खालच्या लेवलला म्हणजेच VC च्या जवळ असायला पाहिजे. म्हणजे जर ह्या पोझिशन व्हॅरी झालं ना तर डिव्हाइस त्या पर्टिक्युलर कंडिशन मध्ये वर्क होत नाही, त्यामुळे बायस स्टेबिलायझेशन म्हणजे स्थिर करावं लागतं, लक्षात घ्या. तर तर another factor, the value of stability factor should be as small as possible. So what it indicate that stability factor indicate that changing stability of particular devices, it require the more energy to stable it, so that stability factor less indicate that it should be stable in a stable easily, right? That's why stability factor should be less indicate that it should be stable very fastly. That's why any of the devices stability factor must be less, right? Now see, Q point should be affected due to change in temperature. Now see, all of the electronic devices, you know that semiconductor devices, they have more problem of the temperature. Means as the temperature changes, whatever the conductivity of it should be changes. You know about the semiconductor, right? So we know that semiconductor are perfectly insulated at the temperature below than room temperature, right? Means temperature effect on semiconductor is more, so that's why Q point changes with change in temperature, right? That's why we have to be requirement of the stabilization of the bias. Now see, another factor is if the Q point shifted towards the cutoff region or towards the saturation region, we get distorted output. See, when we have to be work as amplifier, right? Then our load line position is center of load line, but due to some region, either your temperature change or any other region, that's why shift your whatever the point that should be shifting towards the downward cutoff region or upward saturation region. So what happen, whatever the signal that should be amplified, that should be noisy, or that should have some of the noisy input, noisy output coming, because all of the signal is not coming at your output. So that's why we have to be required to maintain the Q point. Q point indicate that operating point at center of load line for the application of amplifier. Means when we have to be vary the Q point, it shows that whatever the operation with respect to your devices, that should be changing. That's why there should not be change in the Q point of the particular thing with respect to operation. That's why we have to be need of the transistor biasing. Did you getting transistor biasing? Why we needed ट्रान्झिस्टर बायसिंग ची गरज काय आहे, लक्षात येत आहे का? सगळे एकदा मराठीत सांगतो, लक्षात घ्या. ट्रान्झिस्टर बायसिंग ची गरज काय सांगतो की तुम्हाला बायस म्हणजे काय असतं, तर व्होल्टेज अप्लाय करावं लागतं. ते व्होल्टेज अप्लाय केल्यानंतर त्याचा पॉईंट Q पॉईंट चेंज होऊ नये यासाठी आपल्याला बायस स्टॅबिलाइज करावं लागतं. तर बायस स्टॅबिलाइज करण्यासाठी एक फॅक्टर असतो स्टॅबिलायझेशन फॅक्टर. तो जितका कमी असेल ना तितकं चांगलं असतं, लक्षात घ्या, कारण तो ऍडजस्ट लवकर करता येतो. त्यामुळे स्टॅबिलिटी फॅक्टरची व्हॅल्यू कमीत कमी असायला हवी. त्यानंतर टेम्परेचर चेंज झालं की Q पॉईंट चेंज होतो, लक्षात घ्या, कारण की सेमीकंडक्टर डिव्हाइस टेम्परेचरवर सेमीकंडक्टर डिव्हाइसचा टेम्परेचरवर जास्त इफेक्ट होतो, लक्षात घ्या. त्यामुळं टेम्परेचरनं त्याचा Q पॉईंट चेंज होतो. त्यासाठी तो स्टॅबिलाइज म्हणजे स्थिर करावा लागतो. त्यानंतर Q पॉईंट जर शिफ्ट झाला, म्हणजे समजा अम्प्लिफायर डिव्हाइस असेल आणि तो अपवर्ड गेला किंवा लोअर गेला, तर त्याचा इफेक्ट काय होतो, तर डिव्हाइसची जी पर्टिक्युलर थिंग आहेत, म्हणजे त्याचे पॅरामीटर जे आहेत, म्हणजे आउटपुट जे मिळायचे ते व्हॅरी होतं किंवा नॉइज क्रिएट होते, लक्षात घ्या. त्यामुळे तुमचा बायसिंग पॉईंट हा स्टेबल असायला हवा, लक्षात घ्या. ओके, लक्षात आलंय ना? प्लीज रिप्लाय द्या. लक्षात आलंय ना?
येस सर.
ओके. सी व्हॉट एव्हर द इफेक्ट ऑफ सी, लक्षात घ्या, ज्यावेळेस तुमचा बायस पॉईंट समजा ऑडिओ अम्प्लिफायर आहे, त्यावेळेस तुमचा Q पॉईंट हा सेंटरला होता, पहा इथे सेंटरला होता. पण काही कारणामुळं सेंटरला होता त्यावेळेस काय तुमचं इनपुट असं अप्लाय केलेलं साइन वेव्ह, तसंच तुम्हाला बाहेर म्हणजे साइन वेव्ह अप्लाय केलं तर ते फक्त अम्प्लिफाय होऊन तुम्हाला ॲज इट इज मिळालं. पण जर बायसिंग पॉईंट जर इथं आहे तो खाली सरकला, म्हणजे समजा इथं आला, तर काय होणार आहे, पहिलं पॉझिटिव्ह हाफ सायकल फक्त अम्प्लिफाय झालं, निगेटिव्ह हाफ सायकल कुठं अम्प्लिफाय झालं, त्याला काही भाग हा इलिमिनेट झाला. म्हणजे बायस चेंज झालं, म्हणजे तुमचं बायस चेंज झालं की काय होणार आहे, ऑपरेटिंग पॉईंट चेंज होणार आहे. म्हणजे तुमचं जे इनपुट आहे ना ते फक्त अम्प्लिफाय होईल काही पार्ट, कारण त्यातला काही पार्ट हा इलिमिनेट होईल, लक्षात घ्या. जे तुमच्या सिग्नलमध्ये डिस्टॉर्शन क्रिएट होतात इफ द बायस पॉईंट इज चेंज्ड. दिसतंय तुम्हाला? ओके, दिसतंय ना डायग्राम मध्ये? पहा, अशी सिग्नल मिळाला पाहिजे पण अशी मिळते. म्हणजे तुमचा बायस पॉईंट चेंज झालेला आहे. ओके, what is biasing? Now see, biasing indicate that कुठलीही डिव्हाइस असेल ना त्याला व्होल्टेज अप्लाय करणं म्हणजे बायसिंग म्हणायचं, लक्षात घ्या. तर नॉर्मली बायसिंगच्या डिफरंट मेथड आहेत ट्रान्झिस्टरच्या, अकॉर्डिंग टू द नीड. लक्षात घ्या, अकॉर्डिंग टू नीड आणि काय ऍडव्हान्टेजेस आणि डिसएडव्हान्टेजेस पर्टिक्युलर मेथडचे आहेत, त्यानुसार आपण बायसिंगच्या डिफरंट मेथड आपण पाहणार आहोत. पहा, पहिल्यांदा मेथड आपण पाहणार आहोत बायसिंगची कलेक्टर टू बेस बायस किंवा बेस बायस. ऍक्च्युली 3 मेथड आहेत बायसिंगच्या, फिक्स्ड बायस, कलेक्टर टू बेस बायस आणि व्होल्टेज डिवायडर बायस. राईट, व्हॉट इट इंडिकेट दॅट. पहा, ज्यावेळेस आपण बायसिंग करत असतो म्हणजे व्होल्टेज पर्टिक्युलर डिव्हाइसला अप्लाय करत असतो टू वर्क इन अ पर्टिक्युलर कंडिशन, तर त्याच्या 3 मेथड आहेत, फिक्स्ड बायसिंग, कलेक्टर टू बेस बायसिंग आणि व्होल्टेज डिवायडर बायसिंग. फक्त या 3 मेथडचं मॅथमॅटिकल अनालिसिस आहे, लक्षात घ्या. म्हणजे ज्यावेळेस एक्झामला, लक्षात घ्या, ज्यावेळेस थिअरी एक्झाम होती ना 4-4 मार्काला प्रत्येक बायसिंग मेथड होती, लक्षात घ्या. फक्त मॅथमॅटिकल अनालिसिस असते याची, म्हणजे थिअरी नसते याच्या रिलेटेड, लक्षात घ्या. ज्याच्यावर तुम्ही काय इफेक्ट आहेत ते पाहिजे त्याच्यावर. फिक्स्ड आता यातल्या जे 3 मेथड आहेत ना, फिक्स्ड बायसिंग, कलेक्टर टू बेस बायसिंग and voltage divider biasing. So fixed biasing have some of the advantages, disadvantages. Means all of the 3 methods have its own advantages and disadvantages, right? It should be changes according to the particular biasing configuration. Fixed biasing we have seen. See, above figure shows that the circuit diagram of fixed biasing. Why it is called as fixed biasing? See, in this configuration, through this RB resistance, see, through this RB resistance, fixed supply voltage to the base, right? Means whatever the supply provided to the base, that is fixed through this RB. That's why it is called as fixed biasing. जो काय याला सप्लाय होतो ना VCC कडनं RB थ्रू, जे हा रेजिस्टन्स चेंज होत नाही, लक्षात घ्या. त्यामुळे याची व्हॅल्यू जे याला बायस करायला मिळणार आहे ती फिक्स्ड आहे, लक्षात घ्या. त्यामुळे याला फिक्स्ड बायसिंग मेथड असं म्हणायचं, कारण जे बायसिंग साठी व्होल्टेज मिळते ना ते फिक्स्ड आहे, लक्षात घ्या. आणि या केसमध्ये वी हॅव टू बी फॉलो द 3 थिंग्स. मीन्स वी नीड टू कॅल्क्युलेट ओनली 3 थिंग्स. One is your base current, other is your collector current, and third is your VC. These 3 thing calculation is nothing but analysis of fixed biasing method, right? So calculation of 3 things. IB require input side, right? To calculate the VC, we require the output side, right? And IC required one of the relationship, right? These 3 things we have to be calculate, so that to calculate the base current, it is on the side of input. This is called as input side. This is called as output side, right? So for the calculation of IB, we have applied the KVL. See, we have applied the KVL at input side, right? Input side indicate that this side, right? So start up with this point, plus VCC. So plus VCC minus of IB into RB, and going towards there. You know about the how to apply the KVL. KVL कसा अप्लाय करायचा माहित आहे ना? प्लीज रिप्लाय द्या. ज्या पॉइंट पासून सुरुवात करतो ना तो प्लस पॉइंट धरायचा, आणि जिथपासून आउट ऑफ जातो ना तो पॉइंट निगेटिव्ह, म्हणजे प्लस VCC ऍज इट इज, राईट? प्लस VCC ऍज इट इज. परत IB RB इथनं फ्लो होतो. वरचा पॉइंट जर समजा प्लस केला तर खालचा पॉइंट मायनस असतो. म्हणजे प्लस VCC मायनस ऑफ IB इंटू RB. आता इथं पहा, प्लस मायनस ऑफ सी, प्लस VCC minus of IB into RB, voltage between base to emitter, that is called as VB, right? So plus VCC minus of IB into RB minus of VB. This is the equation for the purpose of your IB, right? So to calculate the IB, this is the equation with respect to IB. To calculate the IB, what we have to do? See, we know that this is the equation. At this equation, we have taking IB into RB one side, right? And taking another side. So minus IB into RB taking another side, it is a plus IBRB, right? Plus IBRB is not minus. So plus IBRB VCC minus VB. See, plus IBRB, which is equal to VCC minus VB, right? So we have calculated the IB. So multiply by RB going another side as a divided. So IB equal to VCC minus VB divided by RB, right? This is the equation for the purpose of IB, right? So to calculate the IC, we know that one of the relationship with respect to IC. IC indicates that collector current is nothing but a beta time IB. So collector current equal to beta time IB, right? So we take out the relationship of the beta time IB. So beta IB, we know that the value of IB is nothing but a VCC minus VB divided by RB. So IC equal to beta times of VCC minus VB divided by RB. This is the equation for the IC. We have calculated the IB, IC. Now calculate the VC. To calculate the VC, it is on output side. So to calculate the VC, we have applied the KVL at output side. This is output side. So start up with this point, plus VCC minus of IC into RC minus of VC, right? See here, plus VCC minus of, minus will indicate plus minus, plus VCC minus of IC into RC minus of VC. See here, plus VCC minus of IC into RC minus VC. Now calculation of VC, that's why VC going on other side. So VC equal to VCC minus IC into RC, VCC minus IC into RC. Like this is the value of VC. So in above equation, we have to be calculate the IBIC and VC. This is nothing but a analysis for the fixed biasing method, right? लक्षात ठेवा, फिक्स्ड बायसिंग मेथड होता ना, त्याच्यामध्ये आपल्याला IB, IC आणि VC ची व्हॅल्यू काढायची होती. लक्षात घ्या, IB ची व्हॅल्यू आपण इनपुटला KVL अप्लाय करून काढली, आउटपुटला KVL अप्लाय करून VC काढली आणि रिलेशनशिप बिटवीन बीटा आणि IB, सॉरी बीटा टाइम्स IB म्हणजेच तुमचं IC असतं, ते म्हणजेच तुमची IC ची व्हॅल्यू झाली. लक्षात घ्या, अशा प्रकारे आपण ते काढलं. लक्षात येते, या प्रकारे 3 व्हॅल्यू काढले. लक्षात आलंय का? प्लीज रिप्लाय द्या मला. लक्षात आलंय का? रिप्लाय द्या.
Yes, sir.
Okay. This is the relationship for the purpose of the fixed bias configuration. Now we have seen the second configuration. Now see, one of the important thing with respect to the this configuration, fixed biasing configuration. See, with respect to fixed biasing configuration, there should be, means your collector current is nothing but a IC equal to beta times IB, right? So all of the things, see, beta time IB indicate that all of the things related to the beta. लक्षात घ्या, beta indicate that current gain. म्हणजे तुमचे कलेक्टर करंट हा म्हणजे कलेक्टर करंट हा बीटा नुसार म्हणजे करंट गेन ऑफ ट्रान्झिस्टर नुसार व्हॅरी होतो. पण लक्षात घ्या, ट्रान्झिस्टर ज्यावेळेस डिझाईन करत असतो ना आपण इन इंडस्ट्री, त्यावेळेस काय असतं की प्रत्येक समजा BC547 हा NPN टाइप ऑफ ट्रान्झिस्टर. लक्षात घ्या, समजा मी तो बनवला, त्याचे बीटा 50 असू शकते. समजा तुम्ही बनवला, त्याचा बीटा सारख्या बीटा, कधी बीटा म्हणजे करंट गेन सारखा नसतो, 60 असू शकतो, 50, 40 असू शकतो. लक्षात घ्या, म्हणजे प्रत्येक ट्रान्झिस्टरचा बीटा करंट गेन हा वेगळा असू शकतो. म्हणजे ट्रान्झिस्टरचा बीटा, ट्रान्झिस्टर चेंज झाले की तो चेंज होणार आहे, सेम कॉन्फिगरेशनचे असले तरी. म्हणजेच क्यू पॉईंट तुमचा सारखा चेंज होणार आहे. लक्षात घ्या, इन केस ऑफ दिस टाइप फिक्स्ड बायस कॉन्फिगरेशन. म्हणजे हे व्हायचं कारण का, की ट्रान्झिस्टर एक होता, समजा तो खराब झाला, दुसरा त्याच कॉन्फिगरेशनचा घेतला, पण त्याचा बीटा वेगळा असेल. लक्षात घ्या, तर त्यामुळे तुमचा बेस म्हणजे स्टॅबिलिटी फॅक्टर चेंज होणार आहे. लक्षात घ्या, म्हणजे तुमचा स्टॅबिलिटी फॅक्टर जर बीटावर डिपेंड असेल ना, तर तो सारखा चेंज होतो. कारण का, खूप फॅक्टर आहे त्याच्यासाठी की तो चेंज होण्यासाठी. लक्षात घ्या, त्यानंतर टेम्परेचरवर सुद्धा बीटा डिपेंड असतो. कारण लक्षात घ्या की ट्रान्झिस्टर सेमीकंडक्टर डिव्हाइस आहे, सेमीकंडक्टर भरपूर थिंगचा म्हणजे टेम्परेचरचा इफेक्ट होत असतो. लक्षात घ्या, म्हणूनच बायस स्टॅबिलाइज करायचं असेल ना, तर ह्या सगळ्या गोष्टी विचारात घ्याव्या लागतात. त्यामुळे फिक्स्ड बायस कॉन्फिगरेशन हे जास्त ऍप्लिकेशनला यूज केलं जाईल, जरी त्याच्यामध्ये कॉम्पोनंट कमी लागतात किंवा कॉस्ट कमी आहेत तरी सुद्धा, कारण की अदर डिसएडव्हांटेजेस खूप आहेत. Now see some of the advantages of fixed bias. It also shows some of the disadvantages. See, simple circuit with minimum component, so it doesn't require the more component to work in a particular thing. Another thing, operating point can be fixed currently in the active region by selecting appropriate value for the RB. Only thing is that here we have to use this register RB, right? By selecting the appropriate value of RB, it should be used. So RB is used for the purpose of the particular biasing region or particular biasing configuration. म्हणजेच RB जर फिक्स्ड असेल ना तर तुमचा ऑपरेटिंग पॉईंट चेंज होणार नाही. ओके, त्याच्यानंतर हेन्स द फिक्स्ड बायस सर्किट प्रोव्हाइड फ्लेक्सिबिलिटी इन द डिझाईन. आणखीन काय की म्हणजे कमीत कमी कंपोनंट आहेत आणि जर याचा ऑपरेटिंग पॉईंट चेंज होत नसेल तर हा जास्तीत जास्त ऍप्लिकेशन मध्ये यूज करायला फ्लेक्सिबिलिटी आहे. लक्षात घ्या, हे ऍडव्हान्टेजेस आहेत. पण काही आता हे जे ऍडव्हान्टेजेस आहेत त्याच्या रिलेटेड काही डिसएडव्हान्टेजेस आहेत. पहा, IC increases with temperature and there is no control over it. आता सांगितलं IC इक्वल टू बीटा इंटू IB. बीटा कशामुळे चेंज होऊ शकतो? टेम्परेचर चेंज झालं की बीटा चेंज होऊ शकतो, कंडिशन ऑफ नेचरची चेंज झाली की बीटा चेंज होऊ शकतो, किंवा अदर पॅरामीटर चेंज जरी झाले तरी सुद्धा बीटा चेंज होऊ शकतो. लक्षात घ्या, म्हणजे त्याचे पॅरामीटर लगेच चेंज होतात. आणि पुअर थर्मल स्टॅबिलिटी. थर्मल स्टॅबिलिटी म्हणजे काय? स्टेबल नाही. IC इक्वल टू बीटा इंटू IB. बीटा कशावर डिपेंड असतो? तुमच्या गेन ऑफ ट्रान्झिस्टरची. बीटा ट्रान्झिस्टर नुसार बदलतो. लक्षात घ्या, एकाच कॉन्फिगरेशनचे जर जास्त ट्रान्झिस्टर असतील ना तर बीटा चेंज असतो, म्हणजे त्यामुळे स्टॅबिलिटी याला कमी आहे. देन हेन्स IC डिपेंड्स ऑन IB. हिअर IC इक्वल टू बीटा टाइम्स IB, राईट? बीटा इंडिकेट दॅट करंट गेन. सो collector value depend on the current gain, that is a beta. Beta may change from transistor to transistor. Now see, we know that I already told you beta indicate that current gain value, same configuration. If the configuration is BC547 of one person have the beta of 100, then other same configuration BC547 of beta of 110, right? Means beta of the different transistor have different value. So in this case, stabilization means there should be so many things with respect to your current gain are coming with respect to fixed biasing circuit. These are the some of the disadvantages of fixed bias circuit. Now see, collector to base bias. Collector to base biasing method, what it indicate that? See, this is the configuration. Above figure shows that the configuration which is called as collector to base. This is your base, sorry, this is your base, this is your emitter, this is your collector. So voltage applied in between your collector and the base, right? Collector and the base, that's why it is called as collector to base biasing, right? So for in this configuration also we have to be calculate the three things. One is nothing but a base current, second is your collector current, and third is nothing but a VC. Only three things calculation is nothing but a particular analysis of the collector to base biasing method. It also called as collector feedback method. This send the feedback to the base. Collector send feedback to the base. That's why it is called as collector feedback method, right? So in this configuration we have also calculated these three thing value: IB, IC, and VC. So IB is related to the input, IC is related to the equation, that is beta time IB, and the VC is related to the output, right? So when we have to be calculate the IB, in that case we have applying the KVL at input side. This is nothing but an input side, right? So start up with this thing, right? So start up with this thing. This first point is positive, plus VCC, then going towards the here, right? There are two current with respect to it, because base, this is nothing but a base current, this is nothing but a collector current. Two current added with respect to it, that's why IC plus IB. So plus VCC minus of, see, minus of, why minus? Because plus point lower is minus point. So plus VCC minus of IC plus IB into RC, right? Then minus of here, then minus of, because we have see the thing with respect to input. C plus VCC minus of IC plus IB into this resistance RC, minus of this current IB. So minus of IB into RB. Now see, minus of VB. See this. So it is nothing but a plus VCC minus of IC plus IB into RC, then minus of IB into RB minus of VB. This is the equation which is equal to 0, right? So this is the equation. So that to calculate this thing, we have to be separate out something. So this is the equation. VCC and VB we are taking separate out. So VCC minus VB as it is here. This all thing going another side. So VCC minus VB as it is equal to minus of IC plus IB going another side as a plus of IC plus IB into RC. This minus going another side plus. So it is a plus of IB into RB. This is the equation. So VCC minus VB which is equal to IC plus IB into RC plus IB into RB. This equation coming. Now see, this is the VCC minus VB IB into RC. See, these two things multiply by this, right? So it is nothing but a VCC minus VB which is equal to IC into RC, IB into RC. See, IB into RC, IC into RC, IB into RB as it is, right? So we know that one of the equation IC equal to beta times IB, right? IC equal to beta times IB, right? So VCC minus VB which is equal to IB into RC and IC. For the IC we have to use beta times IB. So IC equal to beta times IB into RC as it is, IB into RB as it is. Now see, in all of the equation we have to be calculate the common as IB. So VCC minus VB, IB into bracket of RC, then beta into RC plus RB. These are the things, right? So VCC minus VB which is equal to IB into RC. In this we have to be common out the RC. So RC 1 plus beta plus RB. This is the equation. Now VCC minus VB which is equal to IB into now see 1 plus beta as it is RB we are taking as addition first, RB plus 1 plus beta into RC. इथं आपण काय केलंय, ही टर्म पलीकडे घेतलेली आहे फक्त का ते सांगतो. लक्षात घ्या, VCC मायनस VB ॲज इट इज, IB आहे तसं. आता इथलं काय केलं, ही टर्म पलीकडे घेतली, म्हणजेच याच्यातलं हे असं करायचं कारण काय, तर आपल्याला RC कॉमन काढायचं आहे. लक्षात घ्या, RC ॲज इट इज कॉमन काढलं, 1 येणार, 1 प्लस बीटा आणि RB ॲज इट इज, राईट, ॲज इट इज. सो VCC मायनस VB इक्वल टू IB इंटू हे RB इकडे घेतलं, RB प्लस RC इंटू 1 प्लस बीटा, राईट, हे इक्वेशन. आता यातलं आपल्याला IB एका साईडला पाहिजे, IB आहे तर ठेवायचं, हे मल्टिप्लाय पलीकडे जाऊन डिवायडेड होईल, म्हणजेच काय होईल, IB इक्वल टू VCC मायनस VB डिवायडेड बाय RB प्लस 1 प्लस बीटा इंटू RC, हे इक्वेशन येईल. लक्षात घ्या, म्हणजेच तुमचं IB कॅल्क्युलेट केला आपण. IC करायचं असेल, लक्षात काही सुद्धा करायचं नाही, IC साठी फक्त बीटा टाइम्स IB, बीटा टाइम VCC मायनस VB RB प्लस 1 प्लस बीटा इंटू RC बाय बीटा टाइम, हे इक्वेशन म्हणजे तुमचं IC कॅल्क्युलेशन झालं. तर VC काढण्यासाठी आपल्याला KVL जो आहे पहा, तो आउटपुट साईडला अप्लाय करावा लागेल. KVL म्हणजेच काय येईल, प्लस VCC मायनस ऑफ IC प्लस IB इंटू RC मायनस ऑफ VC. ओके, VCC मायनस ऑफ IC प्लस IB इंटू RC मायनस ऑफ VC. लक्षात घ्या, हे मायनस पलीकडे घ्यायचं, VC इक्वल टू VCC मायनस ऑफ द IC प्लस IB इंटू RC. हे इक्वेशन VCC साठीचं झालं. ओके, तिसरं होणार नाही आता. याच्याबद्दल आताच एक 2 मिनिटात सांगा मला, आता जे 2 झालेत ना त्यापैकी कोणाला काही प्रॉब्लेम आहे का, आपण रिपीट करू तोच पार्ट. प्लीज रिप्लाय द्या लवकर. पहिलं कॉन्फिगरेशन फिक्स्ड बायसिंग मेथड होतं, याच्याबद्दल कोणाला काय प्रॉब्लेम आहे का, एखादा पॉईंट कळला नाही किंवा काय, प्लीज रिप्लाय द्या, फास्ट रिप्लाय द्या. लक्षात आलंय ना फिक्स्ड बायसिंग सर्किट?
Yes, sir.
ओके, कलेक्टर टू बेस बायसिंग बद्दल याच्यात फक्त एक लक्षात घ्या, इथं IC प्लस IB, फक्त ICच का नाही इथे याचा रिझल्ट सांगतो. आपण फीडबॅक यूज केलाय बेस टू द कलेक्टर, लक्षात घ्या. मग करंट सुद्धा फीडबॅक मध्ये येणार आहे. त्यामुळे इथं इथला करंट म्हणजे बेस करंट आणि इथला करंट म्हणजे कलेक्टर करंट आहे. इथं दोन्ही करंट येणार आहेत कारण फीडबॅक असल्यामुळे. त्यामुळे इथे व्हॅल्यू आली IC प्लस IB. त्यामुळे इक्वेशन असं येते IC प्लस IB याच्या कॉमन मध्ये यायचं कारण की फीडबॅक मध्ये करंट आहे, लक्षात घ्या. ओके, अटेंडन्स देता. रोल नंबर 1, रोल नंबर 1, 2, 3,
Present.
4,
Present, sir.
5, 6, 7, 8, 8 प्रेजेंट का? 9, रोल नंबर 9, रोल नंबर 9, रोल नंबर 9, 10, 11, 12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15, 16,
Present, sir.
17,
Yes, sir.
18,
Yes, sir.
19, 20,
20 present, sir.
okay, 21,
Present, sir.
22,
Present, sir.
23,
Yes, sir.
24,
Yes.
25, 26,
Yes, sir.
27, 28,
Present, sir.
29, 30,
Yes, sir.
31, 32,
Present, sir.
33,
Yes, sir.
34, 35,
Present, sir.
36, 37, 38,
Yes, sir.
okay, 5, 6, 7, 8, 9, 10, 11, 15, 19, 25, 27, 29, 31, 34, 36, 37 absent. Okay,
10.
10 present. Okay,
Sir, roll number 9.
9 per. Okay, okay. 5, 6, 7, 8 परत एकदा सांगतो. 5, 6, 7, 8, 11, 15, 19, 25, 27, 29, 31, 34, 36, 37. Okay.
Sir, 6 number present.
5 present.
5, 6 प्रेझेंट आहेत का? ओके, 5
Yes,
प्रेझेंट,
sir.
5 प्रेझेंट आहे.
Yes, sir.
ओके ओके, स्टॉप करूया.
22 present, sir.
22
हाँ, sir.
22 प्रेझेंटच आहे.
Hello.
हा प्रेझेंट आहे. 22 प्रेझेंट आहे. स्टॉप करू, प्रेझेंट आहे.